Good afternoon, everyone, and welcome to the latest SCLF webinar. For those who don't know me, my name is Alison Mackay and I'm the current chair of SCLF. So it's very nice to see you all here today. And I'm joined today by Matt Askin, who's behind the scenes, and together the two of us will look after you today in terms of the backstage stuff. So if you do have any technical questions, then just stick them in the question box and we'll try and get them sorted. So just before we get started, just got a few housekeeping things and an announcement for you. So you will have joined today on mute and your camera is off, so you can just sit back and relax and enjoy today's session. If you do need to step away, we are recording this session, and so it will be on our YouTube channel probably later today, and I'll put a link for that in the chat in a minute. If you do have any comments or questions for our speaker today, then if you just put them in the question box and we will try and get through as many as we can at the end of the presentation. And if we don't manage to get them answered live, we'll try and answer them offline. And the last of the housekeeping is that when you quit out of this webinar, you will be asked to fill in a wee short feedback survey. We'd be really appreciative if you would be able to fill that in. It should take you no longer than a couple of minutes. The only announcement I have is that we have our abstracts closing today at 5 o'clock for the conference, provisional date of the 31st of August. If you go onto our website, you'll be able to see all the information on there, and again I'll put that in the chat in a minute. So that's call for abstracts to speak at our conference. There's two different types of talks. You can do either a 20-minute talk or a 5-minute lightning talk, which is ideal for early careers or students. So without further ado, I'll just introduce Jack briefly. So Jack is a Senior District Manager for Regenesis in the UK and Scandinavia, and I'll put his full bio in the chat in a minute. And he's going to speak to us today on integrated remediation strategies, expediting the remediation of groundwater impacted by petroleum hydrocarbons. So I'll just hand over to Jack now, and thank you very much for joining us today.
No problem at all. So, hi everybody. Yeah, my name is Jack Shaw. I'm the District Manager for the UK and Scandinavia in Regenesis. And I've been invited today to talk about different in situ remediation options for groundwater that is impacted with petroleum hydrocarbons, including BTECs and PAHs and fuel oxygenates as well. As part of this talk, I'm going to walk you through different injectable technologies that can be utilised to treat this sort of impacted groundwater in situ. But before I get to that, I'll just walk you through who Regenesis are and what we do as a company. So as a company, what we do is we specialise in the research, development and commercialisation of injectable substrates to remediate contaminated groundwater. Today, the focus of this talk is going to be on groundwater. We're a US-based company. We were first incorporated in 1994, and before Regenesis, nobody injected any proprietary reagents into the subsurface. We were the first company to research, develop and commercialize these sorts of technologies. And we've been in Europe since about 2004, and the technologies that I'm going to talk about today are certainly used every working day across the UK and Europe. We've done over 4,000 projects across the EU, nearly 2,000 projects within the United Kingdom. So none of this is new or untried or untested within the United Kingdom. We are going to focus on hydrocarbon technologies, but we also have a suite of other technologies that can treat chlorinated solvents, PFAS, pesticides, and other types of organic contaminants as well. Now, when choosing an injectable substrate to remediate contaminated groundwater, there is a number of steps that you need to take. One is that you need to make sure that the technology that you're selecting is appropriate for your site. Something that I spend a lot of my time doing is reviewing different sites after the site investigation has been completed. We've established that there's a risk to controlled waters, to see if the technologies that are out there match what the requirements are of your particular site. If we do, we'll help you with a technology selection. Now, when you're selecting different in situ technologies to remediate hydrocarbon impacted sites. It's going to be a bit of a balance between the technical aspects of your site. So we are interested in the CSM, for example, but you also have to think about time as well and budget. Often it's a balance between, do you want something done very quickly or do you want something done fairly inexpensively? And to balance those two options when deciding what kind of technology you're going to undertake, you're going to take forward. We'll then provide you with a remediation design, product implementation, and then the post-evaluation is often done by, well, is always done by others. All the case studies that I'm going to talk about today are validated by third parties, so an incumbent environmental consultant or a remediation contractor. But as a company, we do like to stay involved. We like to see it when projects go well. Equally, if you do have a recalcitrant area on your site, it gives us the opportunity to go in and tweak things and correct that. So when it comes to injecting products into the subsurface or getting different chemicals into the subsurface to remediate polluted groundwater, there's a number of different ways that you can do this. The first is direct push injection. So this is where you hammer a hollow stem rod into the subsurface. On the end of that rod is an injection tip with a non-return valve. You hammer it to the depth that you require, inject these reagents under pressure, and then withdraw that rod and move on to the next injection point. In some instances, direct push injection isn't appropriate, and then in these cases we can utilize injection wells. Now this is particularly useful if you're using a technology that isn't just a single application. We're going to talk about chemical oxidation in a second and why sometimes you need to go back and do multiple applications. On sites like this, the installation of dedicated injection wells can be useful. It can reduce application costs. And if you are looking to treat an aquifer that's a solid bedrock, often you can't drive direct push injection rods into bedrock. So again, we would recommend that you use injection wells. Now, these injection wells, they're no different to your standard monitoring well. The only difference is that the top meter of the backfill, we recommend that that's cement rather than bentonite around the standpipe of the well. The reason for that is these products are going to be injected under pressure, typically around 2 bar of pressure. And what we don't want to see is the product erupting up the well annulus and then coming to the surface. We refer to that as daylighting. Other ways to treat hydrocarbons in situ is to apply different reagents to the base of an excavation. However, you'll notice that this excavation extends to the top of the groundwater table. This is something that's important. All of the technologies that we're going to talk about today need to be hydrated in order for them to work. And finally, as I say, this talk is really focusing on groundwater remediation, but sites where you do have soil impact and you're looking to maybe expedite bioremediation, or if you're doing ex situ biopiling, then you can mix oxidants into the soil to drive those those contaminant concentrations down and to create an environment that's more favorable for biodegradation to occur afterwards. So that's what it looks like in practical terms when you're injecting different products into the subsurface. What about what to use where? Now, when we think about hydrocarbon treatment, particularly groundwater treatment, often we have to deploy some sort of integrated remediation treatment strategy. Now, injectable substrates are not going to be a panacea for groundwater remediation. There are going to be sites out there that you absolutely can't help, that they can't help you with. Such sites would be where you have lots of free phase product. So along here, along this axis, you've got contaminant concentrations. On this end, you're looking at mobile free phase NAPL. You then go down to lower dissolved phase concentrations, and then you're looking at treatment efficiency running along the side. Sites where you do have free phase NAPL that is mobile and recoverable, the most efficient and appropriate thing for you to do on that site would be to dig it out or to deploy some sort of pump and treat system to recover as much of that mobile mass as possible. Now, the thing is with physical treatment, is that as those concentrations start to drop, so does the treatment efficiency of that particular method. So an analogy for this would be a pump and treat system that may be running for decades that had reached asymptotic recovery of dissolved phase hydrocarbons. As those concentrations start to drop, as you remove as much of that mobile NAPL as possible, the efficiency of that particular method starts to drop off. Now you can augment pump and treat systems as an example using chemical oxidants, so to enhance the desorption rate so that then your recovery of free phase product increases, but that will only take you so far. As we move down this treatment train, you can then drop on to chemical oxidation. Now, chemical oxidation uses a chemical oxidant to oxidize contaminants in situ. We have a technology called RegenOx that does this, but the process of chemical oxidation relies on contact. The oxidant and the contaminant must make contact with each other in order for that exchange of electrons to occur. So we typically reach for a chemical oxidant on sites where there's no mobile measurable NAPL left. It might be that you then desorb some after the first application. Or we're looking at sites where you've got something like 15 to 50-ish milligrams per litre of TPH in the subsurface. So concentrations that would suggest free phase, but you're not seeing any, you're not picking up any in your well. When I say 15-ish milligrams per litre, I'm talking about a mixed diesel gasoline plume. If we were looking at just diesel or just kerosene or maybe different gasworks constituents, these numbers don't quite stack up. But in this example, we're looking at a mixed diesel gasoline plume. The thing is, as those concentrations start to drop, as you do chemical oxidation, the probability of that contact occurring starts to drop off as well. So as the concentrations start to drop, probability of contact starts to drop, and then the treatment efficiency starts to drop. So it's at around 10-ish milligrams per litre of petroleum hydrocarbon contamination that we can reach for something like ORC, our oxygen releasing compound, to enhance the rate of bioremediation. And then finally, there's a third option, the utilization of colloidal activated carbon to absorb and biodegrade contamination anaerobically. So it sits somewhere in the middle between chemical oxidation and enhanced aerobic bioremediation. And that's what we're going to talk about today. So we're going to look at what we can do in the source zone, so a combination of chemical, physical, and biological treatment. What you can do in, say, the inner core of the plume, it might be a treatment of RegenOx and ORC, and then what we can do to manage that distal end of the plume, the installation of injectable permeable reactive barriers, for example, using colloidal activated carbon that could be supplemented with an electron acceptor such as ORC. So we're going to talk about chemical oxidation first, and specifically around a technology called RegenOx. I'm going to spend a little bit of time on what chemical oxidation is and the chemistry behind it. So first of all, chemical oxidation, often referred to as ISCO, is the in-place treatment through the addition of a chemical oxidant. It's a non-biological process. I often hear ISCO and bio used interchangeably. These are two very different processes. One, we're relying on a chemical reaction to facilitate the destruction of contaminants. The other, we are relying on a biological process to degrade that contamination in situ. I mean, yes, that biological process is a chemical reaction of sorts, but it's facilitated through a biological process. Chemical oxidation then is the redox reaction between the chemical oxidant and the organic contaminant, which is becoming oxidized. There's a number of mechanisms that sit behind chemical oxidation, either direct oxidation or free radical oxidation, and we're going to talk about those mechanisms in a couple of slides. And it's a very useful tool, particularly if you are dealing with a site where the remediation driver is redevelopment. You're looking to remediate your site as quickly as possible. It will destroy contamination very rapidly, and it is well suited to high concentration areas, again, because of that contact that I was talking about before. In Regenesis, we often use it as a mass reduction technique, so to reduce contaminant mass to levels where bioremediation is then more amenable. Historically, though, chemical oxidation used to be quite a difficult thing to do. There was a lot of health and safety concerns around the use of commodity chemical oxidants. So oxidants that weren't engineered specifically for groundwater remediation. In some instances, you would see a rapid increase in temperature and pressure. What I'm going to show you is a video that was sent to me by a client, not in the UK, where it had a lot of experience utilizing RegenOx for ISCO jobs, but then was specified to use a commodity oxidant to remediate this particular site. And you can see what I mean by rapid increases in temperature and pressure. So this was not a RegenOx that was used on this site, it was another commodity-based oxidant. What you can see here is that the oxidant has increased the temperature. You can see the steam coming off of those where the groundwater is bubbling, so we're boiling groundwater here. Increase the temperature and pressure significantly in the groundwater below. You can see here they've had to put up a sheet to stop the mud splashing people that would be walking by the site. And they phoned me up to ask, what is it that we can do about this? You know, this wasn't one of our technologies, but what can we do to ameliorate this? Unfortunately, I couldn't really help them out. And I was told that this reaction continued across the weekend after they'd done this application. This then obviously has risks to burns and personnel and issues with integrating with pump and treat equipment and underground infrastructure. So we really developed RegenOx as a much safer alternative to remediate petroleum hydrocarbons in situ. In terms of what it is and what the mechanisms are behind chemical oxidation, this is a bicarbonate-based chemical oxidant. So this is often it's a white powder that you then mix with water, and then you have part B, which is this iron silicate catalyst. You mix it at about 5% with water, and then you can inject it into the subsurface, targeting your aquifer as needed. In terms of your injection thickness, often this depends on the particular type of hydrocarbon mix that you have. There was a really good study, and actually I'll maybe post this in the chat after the end of the presentation, that was done in Texas, looking at something like 500 different sites where an underground storage tank had leaked. And they were looking to see if there were any similarities between various plumes, various hydrocarbon plumes. And what they found was that if you had a diesel leak, so if what you were recording in your groundwater was a diesel-based hydrocarbon, then you could expect the thickness of the plume, so how much dissolved phase have you got, to extend from 0 to about 1 meter below the groundwater level, because diesel is less soluble than gasoline. Gasoline had a treatment thickness of about 3 meters. So that's a very rough rule of thumb that we use in Regenesis when designing these sorts of application systems. Often you will have underground infrastructure on your site that could act as a preferential pathway, a particular problem on petrol filling station sites. So with carbonate-based chemical oxidants, you can inject them in and around these underground structures. So in terms of the chemistry behind this, so chemical oxidation as a process is the breakage of a chemical bond and the removal of electrons. And there's a number of different ways this is done. The first is direct chemical oxidation. So this is where the oxidant makes direct contact with your contaminant. You have this exchange of electrons. The contaminant becomes oxidized, the oxidant becomes reduced. Those chemical bonds are broken apart and the contamination is destroyed. The second is through free radical mediated oxidation. So the oxidant in the presence of ambient salts will start to degrade. And as it degrades, it will release these things called free radicals. Now, there's lots of different types of free radicals. People, get very specific about them. But essentially, free radicals are just highly reactive molecules without a paired electron. They will react with anything. So there may be oxygen sinks in the groundwater that you'll have to take into account when you're designing an oxidation chemox strategy, but they will also react with your contaminant as well. So when they make contact, you get that exchange of electrons, those bonds are broken, and the contamination is destroyed. Finally, surface-mediated chemical oxidation. So often, and it's the case for RegenOx, the oxidant is activated in some way. In our case, it's base activated, but that rise in pH is only temporary. It's quickly buffered out by the soil. And as that pH starts to reduce back to neutral, the part B, so this is the catalyst that we have, will start to precipitate an iron sulfide catalyst, where the contaminant and the oxidant can make contact with each other on the surface of that catalyst. So it's about keeping that oxidation reaction going. Often there'll be a requirement to undertake multiple applications of a chemical oxidant, be it RegenOx or anything else. The reason for this is that chemical oxidation as a process primarily occurs in the dissolve phase. So when you inject an oxidant into the subsurface, it will reduce your contaminant mass in the dissolve phase in the water, but you will have created a concentration gradient. Now, Flick's law then says that you get diffusion, so that contamination that was previously bound to the soil can rebound then onto the groundwater. Sometimes it will go back to baseline. In some cases, it may actually exceed baseline, and that would be a cause to maybe undertake some sort of physical remediation. So let's take advantage of this desorbed mass to try and recover as much of it as possible, if it's practical. When we see this rebound, we then take advantage of it. So we undertake another chemical oxidation exercise again, typically 2 to 3 weeks after an application of RegenOx, for example. You reduce that dissolve phase mass. You'll still get some desorption, but that rebound will be significantly less. You undertake a third application of, say, RegenOx. You reduce that contaminant mass down even further, and by now we're at a position where bioremediation can take over. And because we've reduced that mass in the subsurface, the probability of contact occurring would be negligible between the oxidant and the contaminant, so we would need to then move on to bioremediation if we had stringent dissolve phase targets to hit, which nowadays is quite unusual across the UK. In terms of the biological element, it used to be thought, people would often say to me, surely doing a chemical oxidation event would wipe out all of the microbes in the subsurface and make bioremediation or other natural attenuation processes to be very difficult to get going. It would negatively impact the natural attenuation processes. Now, this is something that simply isn't true. It's very hard to sterilize anything. It's very hard to sterilize a kitchen table, let alone the soil underground. So what often happens is, yes, these microbes, they do occasionally take a bit of a knock. Let me just get my pointer up. Will take a bit of a knock, but they quickly rebound. I mean, these things grow exponentially. So 2 become 4, become 8, for example. So they'll quickly rebound. Also, what you will have done after doing chemical oxidation is that you will then have some partially chemically oxidized petroleum hydrocarbon molecules in the subsurface, as well as benzyl alcohols and different acids that are much more bioavailable than the contaminant that you started with. So you've actually given these microbes a meal that's easier for them to digest, is the simplest way of thinking about it. Another byproduct of this reaction will be an increased amount of oxygen in the groundwater as well. Now, these microbes that degrade petroleum hydrocarbons in the subsurface will preferentially use oxygen as an electron acceptor. As I'm sure everybody on this call knows, under aerobic environments, you will degrade hydrocarbon contamination much quicker. But the thing is that chemical oxidation event will only temporarily increase those oxygen levels in your aquifer. As they are used up, as that oxygen is used up, the rate at which that natural attenuation process is occurring will slow down. So to prop that up, you could then inject another compound, such as ORC, an oxygen releasing compound, to maintain those aerobic conditions to keep that biological degradation accelerating. Now, these microbes that are breaking down contamination in situ, what they're doing is they're cascading electrons from donor compounds. So this is the hydrocarbon, so the contaminant in this case is the donor compound, to receptor compounds. So this is oxygen, nitrate, iron, sulfate, carbon dioxide, etc. in a respiration reaction, and it's that exchange of electrons that releases, gives free energy, and that gives the microbe the energy that it needs to live. Now, the payoff that they get from these different electron acceptors differs. So oxygen, it gets much more energy than if it uses sulfate, for example. The electron donor, the availability of the food, the more soluble it is, the easier it is for these microbes to break it down. So it's why if you're dealing with a mixed diesel gasoline plume, the gasoline fractions often go much quicker. So to facilitate this respiration reaction, you can apply ORC into the subsurface. ORC is a calcium oxyhydroxide that we've interpolated a phosphate crystal into its structure. What that means is when you apply something like ORC into the subsurface, it will start to dissolve. And as it dissolves, it will release dissolved phase oxygen into the groundwater. Now, that's really important. What you don't want from a compound is lots of bubbling and off-gassing. You don't want the oxygen escaping to the atmosphere, because if it does that, that's not where these microbes can utilize it. So the rate at which this dissolution happens is controlled and regulated by these phosphate crystals. These phosphate crystals also have another purpose. They stop an impermeable rind forming around the calcium oxyhydroxide. That then disrupts this crust forming that ensures that after a single injection of ORC, you get up to 12 months worth of oxygen released over that period of time. Now, this is really important. What we're looking to do here is enhance the rate of natural attenuation, enhance the rate of biological degradation. And to do that, what you need to do is farm microbes. And the best way to farm anything is to give them plenty of food and to keep their environment consistent. What you don't want to do is be doing lots of injections, spiking the aquifer, crashing it, spiking it, crashing it. It's not going to create this stable and sustained environment over a long period of time. You want a stable environment over a long period of time that's optimal for biological growth, so you can grow as big a microbial consortia as possible, so that these contaminants can then be broken down in situ. Now, often the remediation program is one of the key things. People want the site remediated very quickly so that they can get on and build, for example. It's less important if you are dealing with an industrial client that maybe is just looking to mitigate liability. But a lot of sites that we see, most of the sites in the UK that we see, are driven by redevelopment. And one of the things about biological degradation, enhanced biological degradation, is that it's relatively straightforward to work out how much oxygen we need to introduce into the subsurface. So the stoichiometric demand that is required to break down a mass of petroleum hydrocarbon contamination. And also how we get it into the subsurface, how we distribute it, is relatively straightforward as well. However, predicting when you're going to hit a particular remediation target can be quite challenging. And this is down to the nature of these microbes themselves. So the microbes that are responsible for breaking down petroleum hydrocarbon contamination in the subsurface, they're not planktonic. So the analogy is they don't like swim around in the aquifer, sort of seeking out petroleum hydrocarbons to eat and break down. They're sessile. So they sit on the aquifer matrix and they secrete something called a biofilm. And as the contamination advex and diffuses through the aquifer, it's the job of this biofilm to capture that contamination and then break it down in situ. So my analogy now is that they're more like sea sponges. I used to say sea anemones, but I think about 300 Swedish people pointed out to me that sea anemones actually move around the sea. I didn't know that, didn't grow up on the coast. But yes, they're more like sea sponges. They have to wait for their food source to come to them. So to take advantage of this, you can utilize colloidal activated carbon. And one of the technologies that we have is Petrofix, which is a colloidal activated carbon. What we have done is we finely milled granular activated carbon down to 1 to 2 microns. So that's the size of a bacterium, about the size of a red blood cell, smaller than a pore throat in the aquifer. And we've coated these activated carbon particles in a dispersive polymer so that they move and behave like a colloid. So blood is a colloid, wine is a colloid. These things flow very freely in the aquifer matrix. There's a second part to this product. So this is an electron acceptor blend that comprises nitrates and sulfates. So what we're looking to do here is absorb contamination and then degrade it anaerobically. Now, earlier I said degrading petroleum hydrocarbons using oxygen is the fastest way to do it, and that is still true. Why then would you use sulfates and nitrates? In this instance, we absorbed the hydrocarbons onto the petrifix, so we've broken that source pathway receptor linkage, effectively buying you then the time to undertake anaerobic biodegradation. And it also has some advantages as well beyond speed, so that are not speed. Where this technology can't help is that it can't stop surface migration of contamination. So you can't use this in to replace a boon, for example. We've had instances of people trying to do that and it doesn't work, and we would never recommend to do that anyway. And we also can't stop free-phase contamination. So those of you that are familiar with pump and treat systems, for example, you wouldn't put your granular activated carbon filter at the beginning of your treatment train. You put it at the end, after the oil water separator, after the settling tank, after the sand tank. So the same goes with petrifix. It can't stop mobile free phase contamination. If it does encounter free phase, what it means is that the NAPL will just move through the barrier, and then it will take a while for that smeared NAPL to be degraded using under anaerobic conditions. It's very easy to use, so it's a water-like suspension. The base ingredient of this is activated carbon, so it's non-hazardous. It's made of the same stuff as your Brita water filter. So the remediation process initially is absorption. So this is a before shot that you can see in the bottom left-hand corner. And these are your sand grains, very flat, not a lot of absorption sites. After you inject something like petrifix into the subsurface, petrifix will coat the subsurface with activated carbon. And what you're looking to do when you're applying it to the subsurface is for it to travel along your flux zones. So you're looking for it to travel along your flux zones, absorbing any contamination in your mobile porosity, but also then coating the outside of your immobile porosity. So you can absorb contamination as it migrates from upgradient of your injection site, but also by coating your immobile porosity with petrifix, you are then mitigating against back diffusion from that secondary source of contamination. The second step then is biodegradation, and then the third is regeneration. So when you apply petrifix to the subsurface, what will happen is that with an electron acceptor mix, and that could be ORC, that could be the nitrates and sulfates that I mentioned earlier, you will encourage the growth of the microbes that are breaking down that contamination. Now, as I said before, these microbes are sessile. The contamination, however, is stuck to the petrifix matrix, so the microbe's food source and the microbe are together on the same surface. We've added an electron acceptor blend so that we've created the conditions that are optimal for these microbes to grow. So the food source is there, right next to them. The electron acceptors are plentiful. You will then degrade that contamination in situ. So you stimulate that anaerobic biodegradation, and as that contamination, those contaminants are degraded, more absorption sites get freed up in the petrifix matrix. That then allows the contamination that might be upgradient of your treatment area to then absorb onto these freshly cleaned off sites. So you can engineer and create a self-cleaning filter in your subsurface using petrifix. This will go on for a very, very long time. In some cases, on some certain sites, indefinitely, as long as there is enough ambient electron acceptors and there is enough contamination to keep this going. This is down to syntrophic biodegradation. This is very much a hot topic at the moment, sort of in the in situ bio community. Syntrophic bio is essentially a community of microbes feeding together. So as microbes break down certain electron donors, they will produce these waste compounds, and these waste compounds can then be used as electron donors by other contaminants. So what's going on is, say some microbes are breaking down petroleum hydrocarbon contamination. When they do that, they produce these waste products. These waste products, if they are allowed to accumulate, can actually create conditions in the aquifer that are not thermodynamically favorable for the degradation of TPH in situ. But by other microbes essentially feeding off of these waste products, conditions stay right for degradation of hydrocarbons in situ. So it maintains this effective long-term degradation sequence. We've seen this in action. So this is some data from a real site that we did where they really went above and beyond in terms of monitoring and validation. You can see here once the Petrofix has been injected with a nitrate and sulfate blend. I'll just mention the reason why nitrates are in there. Microbes that degrade BTEX, specifically benzene, will use nitrates as electron acceptors preferentially over other compounds. The nitrates are in there because often it is benzene that's driving the risk when it comes to hydrocarbon treatment, so we're looking to knock that out pretty quickly. I think benzene was the first identified carcinogen, but anyway, that's why nitrates in there. So when you apply these electron acceptors, these electron acceptors are quickly used up by the microbes in situ. But actually what you can see is when those concentrations of electron acceptors reduce back to baseline, we still see an ongoing increase in both the number, so the cell count of microbes in the subsurface, but also the biodiversity as well. This indicates that you then have syntrophic bio ongoing. So that Petrofix treatment will effectively keep this regeneration cycle going, mitigating against the off-site migration of mitigating against any hydrocarbons breaking through a Petrofix treatment area. So what does this look like when you use all of these technologies together? So this is a site in Sweden. It's in a place called Hagelund, which is a suburb of Stockholm in the north. I'm told this building here is called the Friends Stadium. This is very famous in Sweden. I'm not sure if it's very famous anywhere else, but this is the Friends Stadium. And this was the site that we were working on. This is, I'm told, to be the largest rail depot in Northern Europe. And here they had a part of the site where they used to refuel diesel trains, and it was also a workshop area in this building here. In Sweden, they have very stringent cleanup goals, and they're very heavily regulated when it comes to contaminated land. And the operator called Jan Hersen, which translates to Iron House, which I quite like, was tasked to remediate a proportion of their site. So the impacted area was about 7,500 square meters. And here we were dealing with not only LNAPLs, but DNAPL hydrocarbon contamination as well. So in some cases, we had to treat down to 7 meters below ground level in situ. So the total impacted soils that we needed to be treated, the total volume of the aquifer that needed to be treated was about 30,000 square meters. They deployed an integrated strategy here. So they did a site investigation and they discovered significant amounts of LNAPL. So that was removed using multi-phase extraction. This is our treatment area, and I'm not sure if it's totally clear for everybody, but these red dots are monitoring wells. So we had something like 73 validation wells that all had to hit targets below the minimum acceptable criteria for the whole of Sweden. So it was very intensively validated, this particular job. Once they had removed the the free-phase hydrocarbon contamination, they dropped on to utilizing RegenOx as a chemical oxidant. They then finished off with ORC, and they injected Petrofix as adsorption agent. The work's completed. It was pretty extensive. They installed an additional 62 monitoring wells, so they had over 70 monitoring wells to validate these works. They removed something like 40 tons of free-phase hydrocarbons, and this was a really large job. So you can use injectable substrates on jobs that are very, very small. So, you know, I design jobs that range from like £2,000 to £2.5 million, and so this is on the bigger end of this scale. The results from this, so these are this is post injection, so this was a month after the injection works were completed. Here the ground was very much still in flux, but it was somewhat representative of the concentrations before they started injecting, but after they finished their abstraction. Once things had settled down, concentrations dropped off significantly, and then finally, you know, the average TPH from 71 monitoring wells showed a greater than 99% reduction in contaminant mass. In terms of how much does this all cost, this is often a question that's sat in the back of people's minds when I talk about these methods. It's kind of like asking how much does a site investigation cost if you're a consultant, or if you're a contractor, how much does a cut and fill exercise cost? It all very much depends on the site. It's why it's really important to do this evaluation process in the beginning. If you're looking to illustrate to a potential client of yours why you can't answer how much will this all cost, I'd say the Homes and Communities Agency had done, it's a pretty old document now, but had done a pretty good job illustrating how complicated it is to just pull numbers out of the sky for any sort of remediation. Something we try to do though as a company is publish as much information as possible, be this scientific papers or case studies. We have over 200 case studies on our website, easily searchable by contaminant type, product, or even past industry, all free to download. We try and provide you with as much detail as possible, including the cost as well. So where we can, we will offer that level of detail. So yeah, in conclusion, you know, there's a lot you can do with hydrocarbons in situ, sort of beyond excavation and just pump and treat. You could look at augmenting pump and treat systems using chemical oxidants to enhance desorption and recovery using something like RegenOx. Maybe for sites where you don't have any mobile NAPL, chemical oxidation coupled with bioremediation could be a potential option. And maybe for sites where you can't treat the source, or maybe the only driver for risk is to stop off-site migration, using Petrofix as a barrier in combination with an electron acceptor like ORC could adequately mitigate against that risk. So that's everything from me. You know, I appreciate everybody taking the time to listen to this presentation. If you have any questions, I guess this is the time to ask them. But yeah, if you do want to get in contact with me, if you do have a question later on, please feel free to take down my details and reach out then. So thank you very much.
That was great. Thank you very much, Jack. So yeah, if you do have any questions for Jack, I know there was quite a lot in quite a short space of time there for everyone to get their heads around. But I liked all your images and your videos and stuff like that. That was great. But if you do have any questions for Jack, if you want to stick them in the questions box.
Maybe try again, Alison, I think.
Yeah, can you hear me now?
Yeah, I can hear you now. Sorry.
We're back.
That's the webinars I've done. I've never had that happen before, but okay.
No, I've not either, and this is number 32, no. And that's what happened. So. Okay, so yeah, we do have a couple of questions in, but yeah, I'll continue asking my question. What is there any particular data or information that you would like to see coming to you that would help you get the very best design for people?
So as a minimum, we need description of the geology, depth to groundwater, and contaminant concentrations in the area that you're looking to treat. That's sort of the absolute minimum. as much hydrogeological information as you can get, really. So if you are doing if you've done a DQRA and you've established that there's a risk, normally then we have more than enough information to do that. But we can do designs on very little information. There's just more assumptions that we're going to have to make.
Okay, we've got a question from Esther, who's just asking about chemical daughter products created by the chemical oxidation. Is there any potential for volatiles to become more mobile?
So you can, for a very short, very short period, create something called oxy-PAHs, which is sort of an intermediary. But these things are broken down very quickly, and actually, I don't know, thousands of chemox jobs that I've done over the years, I've never actually seen them, but it is a theoretical risk. The biggest risk from doing chemox is desorption of mass. So if you do expect that there is more mass down there than you were expecting, I always say have a watching brief for any NAPL generated, so that then you can recover it as required. That's sort of the biggest risk around chemox.
Okay. Amy just wanted to clarify something. She said that where the site's authorised by SEPA permit, they initially look for a target of a minimum reporting value for groundwater hazardous substances. New values are being derived, but these are also low. So she just wanted to clarify on that. Okay. And we're all eagerly awaiting directions from the Scottish Government so that we can finally get our new PS10. Yeah. But we have no timescales on that as far as I know yet. Any other questions from anyone? Don't see any more coming through. Yeah, in terms of the licensing and regulation, Jack, is that something that you would do, or do the consultants that employ you?
Most of the time it's the consultants or contractors. So Regenesis, we do have a sort of small contracting arm. So if you did want us to do injection works, we could, but forgive me, we don't have what we would call, we don't have an MTL for Scotland, if that makes sense. So we would, normally it's done by a contractor, if I'm honest with you. So we would just sell products in for a contractor.
Okay. In terms of getting a design done by Regenesis, how long would that typically take from when you have all the data in front of you?
It depends who you get. No, it's it can be very quick. So there are instances where I'll do it over the phone. You know, if the question is, we're thinking about Petrofix, roughly how much is that going to cost me? We could do that. We could do something like that over the phone, and then you've got a ballpark figure. For more complicated sites, we tend to ask for 1 to 2 weeks to produce a design. So yeah, but I also appreciate that sometimes things need to be turned around quicker than that. But we try and get everything turned around typically within a week.
Okay. Well, I don't see any more questions coming through, Jack, so that you've obviously done a very good job or stunned everyone into silence. So thank you very much again. And as I said, this if you want to go back and re-watch this, then it will be on our YouTube channel. And remember to get your abstracts in for our conference. Obviously, Regenesis are very welcome to submit an abstract as well if you want to present a case study or something like that. It'd be most welcome. And we'll be in touch soon for our next webinar in a couple of months' time. So thank you very much, and hopefully everybody enjoys the rest of the day. Thank you.
No worries. Thank you so much. Thank you, everyone.